Going to keep that up on the board for our help. So now that we know a little bit of how trig works and how to add vectors, we can now kind of do the opposite, which is splitting vectors into their components, like I was saying before. So if we have some vector, we'll call it R again. R is a good letter for vectors. The most easy to work with components that we could possibly split it into are the x and y. So if we draw a set of axes right here, so when you've got your x and your y, now we can split it into components that act along those lines. So there's going to be a part of it that goes this way and part of it that goes up. And if you remember before, I said tip to tail, and then you start at the first tail and end at the last tip. It looks like this one plus this one will give us r, and that's what we need to happen. So if you need to split a vector into x and y components, it's always going to be the hypotenuse of your triangle. And then we know that the x and the y-axis always make a 90-degree angle, so we can mark it as a right angle. So now we can find out a plethora of things from this diagram if we know something, if we know the angle, or if we know what one of the components is. If you wanted to know a component and you're not using IJK, typically you use a subscript. So if I want the x component, I just say r sub x. If we can relate rx, ry, theta, and r, our lives will be a whole lot easier in the long run. So using a little bit of trig magic, there's this dude that ripped off a ton of work from the people who worked for him, and his name is Pythagoras, and he has a pretty famous theorem. So the Pythagorean theorem, for those of you who might need a little refresher, because it's been a while for me, know that it's a squared plus b squared equals c squared, which really that's not super helpful. So if I put it in terms of this diagram, so that way you can see how it relates to the triangle, rx squared plus ry squared equals r squared. If you notice I didn't put the hats on them, that's because these are all magnitudes, so we don't have to worry about it. So we have this. This is super helpful. If you know the x and the y of something, you can find what that resultant is. So the next thing is to relate some angles. So if we want, let's say we want to find the angle theta and we know ry and r. If we know ry and r, and we want theta, ry looks like it's opposite theta, and r is the hypotenuse. So if we want opposite and hypotenuse, we're going to use sine. It's the way it rolls. So if we use opposite and hypotenuse, we know that the sine of theta, actually I'm going to write this up here. Okay, so we know that the sine of theta is the magnitude of ry over the magnitude of r. This is where, if you need to find theta, you can use the inverse button on your calculator. If you need to find ry or r, you can do a little bit of algebra, solve for that. So if we need to relate rx to theta and r, if we just use sine, you know, you've got a 50-50 between cosine and tangent, and I told you r always has to be the hypotenuse, so we're going to use cosine. So the last one, if we want to relate rx and ry to each other via theta, we are going to use the tangent. I will tell you that the situation you most commonly use this one for is when you're solving for a resultant vector, you always need a magnitude and a direction. Direction can always be given as so many degrees above the x-axis or so many degrees below the y-axis. So that's where you most commonly use this tangent one. You don't use it when you're splitting a resultant into components. However, these guys you can use. I will warn you that with all three of these, if your angle is not a horizontal angle, if it is over here instead of over there, these suddenly all become wrong. So these are not sort of like a catch-all. These are, hopefully you can see the relationships between. So if your angle is up here, then ry becomes your adjacent, rx is your opposite.